Hello, welcome back to Algebra. The title of this lesson is Solving Fractional Equations. This is part one, and there are so many different types and flavors of these things we call fractional equations that we're going to have part one, then part two, then part three, and part four, and so on to give you lots and lots of practice with different types of problems. But the basic idea is we're learning how to solve more complex equations. If you remember, we learned how to simplify these rational expressions. We learned how to simplify what we called complex fractions in algebra, which have weird numerators and denominators. And then in the last few sections, we learned how to simplify equations or solve equations that have fractional coefficients. That sounds very similar to this. This is something different though. It's called solving a fractional equation. And so the easiest way to explain the difference between what we've done before and what we're doing now is literally to go ahead and just put a couple of them on the board and show you. But let me warn you up front, we're going to have three problems. The first two are not difficult at all, but the third one is pretty lengthy. I really want you to make it all the way to the end of this lesson though, because in the third problem, I need to get some groundwork under us, but in the third problem, we're going to introduce the concept of an extraneous root of the equation, an extraneous solution of the equation. What we're going to find out is sometimes we're going to solve these equations and we're going to get some answers. And when we check the answers, sometimes we will find out that some of these roots, some of these answers aren't actually valid solutions. So it's really important that you get to the end so that you can see an example of that, because when solving these kinds of things, we're going to basically have to check and make sure that all of the answers are valid. And so I need to show you an example of when they're not valid. So let's work through some easier ones and get to a more difficult ones here in just a minute. Now, before we show you a fractional equation, let's look at something that we learned how to solve in the last couple of lessons. That would have been something like x over 3 plus 1/2 equals, 1/10 or something. This is what we called a equation with a fractional coefficient. Why did we call it that? Because even though it's written as x over 3, you can kind of think of it, and the way I think of it really is 1/3, which is the coefficient, times x plus 1/2 equals 1/10. Right, so you can see that the coefficient, which is just the number in front of the x, is a fraction. And we learned how to solve those. We had 3 or 4 or 5 lessons solving these equations, what we call fractional coefficients. And the main solution technique was, we said we need to cancel and clear out all of these denominator numbers. We have to multiply the left and the right hand side by something, some number, to kill the 3, to also kill the 2, and to also kill the 10. And you have freedom, right? But I can tell you right now there's choices. You can all have your own choice. You can have your own number in your mind. But I know that I can multiply left and right hand side by 30, for instance. In this case, I know that 30 will work, and that will clear all of the numbers. We did lots of problems like this. So if you don't understand that, then go back and look at those equations with fractional coefficients. If we multiply the left by 30, then the 30 will multiply into both terms, and the 30 divided by the 3 will give you 10. That's a whole number. The 30 divided by the 2 will give you the 15, that's a whole number. And the 30 divided by the 10 will give you 3, that's a whole number. So by multiplying left and right by 30, you eliminate all of the fractions. And the fractions are what make these things a pain to solve, because adding fractions means you have to get common denominators and so on. So that's a trip down memory lane. That's what we did last time. Learning how to solve these things involved multiplying left and right hand side by something to kill the denominators to make it easy, right? Now this is different. This is the kind of problem that we're going to do here, and we call these fractional equations. Fractional equations. Whoops, got to spell right. All right, and so here's an example, our first example of a fractional equation. 3 over t minus 1 over 3 times t equals 2/3. Now take a look at this equation and compare it to the one above. We've solved these kinds of problems before. This is new. See, in an equation with what we call a fractional coefficient, the variable is basically still on the top, right? So all of the denominators of all the fractions are just numbers. So in order to clear away the denominators, all we had to do was pick a number. In this case, we said we'd choose 30, but you could choose another number that also would clear them. And then by multiplying by that number, you would clear all of the denominators because they would divide away, okay? But notice in this one, this is not a fractional coefficient, this is a fractional equation. That means that the variable is also allowed to be in the denominator of the fraction. So notice that the variable is in the top here, but the variable is in the bottom here. It's also in the bottom down here. Now, we could have rolled both of these concepts together, the fractional coefficients and the fractional equations. A lot of students say, Well, they're two different skills, right? Well, they kind of are two different skills, but really what it boils down to more than anything is when you have a fractional coefficient, it's just the easier case because you just have denominators that are numbers. So all you have to do is pick a number to multiply to clear everything out. But now we have something different that looks slightly more complicated, but it's in the same family. It's a fractional equation. The denominators of these fractions can also have variables. That's why we say they're fractional equations. So it's a little bit more challenging, but the same process is going to apply. What we need to do is get rid of these denominators, just like we were getting rid of these denominators. So let me write the equation one more time, and we're going to decide what we need to multiply by. 3t equals 2/3. What we need to multiply by in order to get rid of these denominators. Now, I can multiply anything I'd like, left and right-hand side. Let's say I multiply the left and the right by just the number 3. If I multiply by 3, and I multiply by 3, the 3's would cancel here. That would get rid of that. The 3's would be distributed in and cancel this 3, but it wouldn't affect the t at all. The t's would still be in the bottom, which would make it very difficult to isolate t, get it and divide or multiply. It would just make it a little more difficult to actually isolate t, because in the denominators of fractions, it just makes it hard to collect them all to one side. So what we really want to do is we want to figure out what can we multiply this equation by, left and right-hand side, to clear the 3's, but also at the same time clear the t's. So you guessed it, we want to multiply by 3 times t. If we do it here, we also have to multiply by 3 times t here. Why are we choosing this? Because we know that the 3 will cancel with this 3. We know the 3, once we multiply it all in, will cancel this 3. But once we multiply this whole thing in, the t will cancel with this, and the t will cancel with this. Yes, of course, this t is not going to cancel with anything. It'll still be in the top. But we don't care about introducing things in the top. All we care about is eliminating all denominators, because then we don't have any fractions to deal with, and by now you should know that dealing with fractions is just a pain. You can solve this thing by subtraction, of course, but it's just not as easy. So let's move ahead through it. What we have then, we're going to do exactly the same technique as before. 3t is written as 3t over 1, multiply, distributing it into the first fraction, 3 over t. Then we have the minus sign. 3t will be distributed in as 1 over 3t. So it's distributed into both terms. And then on the right-hand side, we'll have the 2/3 multiplied by the 3t over 1. So now we have some glorious cancellations, right? Because we have a 3 canceling with a 3. Notice I did not strike through the t, it's not gone. This 3 cancels with this 3. This t also cancels with this t. This t cancels with this t. Now, by the way, when I say it cancels, of course, it's in the top and the bottom. But what's really happening is in any fraction, like 6/10 or something, you can divide the top and the bottom of that fraction by anything you want to simplify it. Like 6/10, I might say 6 divided by 2 on the top, 10 divided by 2 on the bottom. I divide top and bottom by 2, right? So when I cancel these t's, what I'm really doing is I'm saying divide the top by t, that gives me 1. Also, divide the bottom by t, that also gives me 1. That's why they poof, disappear. Because I'm dividing top and bottom by the same thing, it gives me 1 in both cases. So now we can cruise along. All I have left, I have nothing on the denominator except 1's. So the denominators just disappear. They're really there, but you're dividing it by 1, so they're gone. 3 times the 3 is going to give you 9. Here's the minus sign. This is a 1 times a 1. So don't forget, it doesn't totally disappear. You still have 1 times 1, so you still have a 1 here. All right? Okay. And on the right-hand side, all you're going to have is 2 times the t over here, and it's divided by 1 as well. So notice you've eliminated all of the variable t's on the left-hand side. The only variable that you have left over of t is on the right. Now you have 9 minus 1, which is 8, 2t. And then you can, of course, divide. So I'm going to rewrite it and say t is equal to 8 over 2. So then you know that t is equal to 4. T is equal to 4. And that is the correct answer. So here's the gotcha. In this very simple problem, it's not going to be an issue, all right? But I need you to kind of go through the rest of the problems with me, because what's going to end up happening is sometimes when you multiply the left and the right-hand side by variables in addition to numbers, sometimes some of the solutions you get at the end of the problem are actually not valid. But I can't show you that it's not valid, because in this case, everything's fine. But work with me through. We have one more problem, and then we have the last problem. The last problem we'll have two solutions we get, but one of them isn't actually valid, and I can't get you there until we get there. So for now, you say, well, t is equal to 4. So the thing you should look at is you should go and plug it back in and see if it causes any problems. So let's do that really quickly. We're going to go back and plug it into this equation. We're going to plug it in to what we started with and just verify that it's right. So it's 3 over 4. Okay, that's what, yeah, because 4 is t, so it goes in here. Then we have minus 1 over 3t, 1 over 3 times 4, because t is now 4, equals 2/3. If everything is correct, then this should actually work out fine. So we have 3/4 minus 1/12 is equal question mark 2/3. 2/3, like this. Now we have to change this from 3/4, we have to multiply 3 over 3 to give it a common denominator of 12. Like this. So we have 9/12 minus 1/12. So what we have here when we get down to this point is we have a common denominator. So 9 minus 1 is 8/12, right? And if you divide the top by 4, you're going to get 2. And if you divide the bottom by 4, you're going to get 3. So you should all know that that's equal also to 2/3. So it's exactly equal to what we had on the right-hand side. So we get a solution, we check a solution, and we see the solution's fine. So then at that point, we can circle it and say no problem. But what's going to happen in the third example here is we're going to get down to the end and we're going to find out that sometimes it doesn't quite work. For these simple problems, it does. So you have to be on the lookout for what we call extraneous solutions, solutions which fall out of the math but aren't valid. So for now, just understand that the concept is the same. We clear the denominators by multiplying by anything we want. Oftentimes we'll have to multiply by variables in addition to numbers, and then we proceed with the rest of the solution as we have done. All right, next problem. If we have, let's say, 1 over x equals 2 over x minus 3, like this, x minus 3, then we want to solve that equation. What do we multiply by? We want to get rid of the denominators. That means we want to get rid of the x, and we also want to get rid of this entire denominator, x minus 3. We don't want to have any denominator here. We don't want to have a 3 here, and we also don't want to have an x here. So let's rewrite it, and let's decide what to multiply by. What do we have to multiply by? Actually, I didn't quite leave myself enough room. Sorry about that. We'll do it like this. 1 over x. What do we have to multiply by on the left and on the right to clear everything? Well, we know that if we multiply by x, it'll kill this. But if we multiply by x, it's not going to kill the whole thing. It's not going to cancel with the whole x minus 3. Alternatively, we can multiply by x minus 3, the quantity x minus 3, which will cancel this. But if we multiply by x minus 3 by itself, it's not going to cancel that. So the solution is we have to multiply by both denominators. We have to multiply by x times x minus 3, which looks crazy weird. But remember, the only thing you're trying to do is cancel those denominators. You don't care how ugly it looks in the top. You just want to clear everything. It's kind of like the nuclear option. You go to multiply by the whole enchilada to clear everything in the bottom. So what we have then is x minus 3 over 1 multiplied by the 1 over x equals 2 over x minus 3. Let me wrap parentheses around this just to group it, times the x minus 3. Now, on the left-hand side, we have an x here and an x here. Those cancel. Notice that this thing we had to multiply by didn't cancel anything on the left, so it's still there. But this x minus 3 cancels with this x minus 3, and notice that this x, which is sitting along here, didn't cancel anything on the right, but that's okay. All we wanted to do is clear all of the denominators, which we have now accomplished. So on the left, we have x minus 3 times the number 1, which gives you x minus 3. On the right, we have 2 times the x. That's all that's left. Now look how simple this equation is to solve. You can, of course, solve that very easily. Let's take the 2x and move it over here by subtraction. So I have 1 minus 2, so it'll give you negative 1x minus 3 is equal to 0. We'll take the 3 and move it over here, so I have negative x is equal to positive 3. We'll add 3 to both sides. And then we'll say x is equal to 3 over negative 1, right? Which means x is equal to negative 3. X is equal to negative 3. Now we think this is the answer. So what we showed in the last lesson, in the last problem, is we take this and we try to plug it in and verify. But really, I'm kind of inching along here to you, what you're really on the lookout for to see if you have an extraneous solution, which means a solution that's not even valid at all, is you just want to really make sure, you don't have to check the problem every single time to verify it's right, but what you really have to do is make sure that the answer you got doesn't cause your equation to blow up to infinity or do something really crazy or not something that's not well behaved. So what you do is you notice that over here you have a -3 for the answer. So you go and you say, okay, if I were to put -3 in here, 1 over -3, is that well behaved? Yes, 1 over -3 is just -1/3. Here, if I put -3 here, it would be -3 minus 3, which would be -6. So 2 over -6, that's also a well-behaved number. It's not over 0, in other words. What you're looking for is if any of these solutions you get, when you stick them back in there, you get a 0 on the bottom. That will cause the solution to go blowing up to infinity, or the equation to blow up to infinity, which means that what you got wasn't really valid at all. It's not allowable, right? So in this case, we take this number, we stick it into both places. We don't even do the math. We just make sure the bottom doesn't go to infinity, and it doesn't. So this is totally fine, well behaved, okay? We go back to this. I showed you the answer was t is equal to 4. We actually plugged it in and verified it was true, but really now I'm telling you that you don't really have to verify it. Just take the 4 and stick it back in. Here you have a t set it equal to 4. Does this go to infinity? No, it's fine. If you put a 4 here, 3 times 4 is 12, right? 1/12 is very well behaved. It doesn't go to infinity, it's fine. But if in some alternate universe, let's say for this answer I got t is equal to 4, but somehow through the math I also got t is equal to 0. That was another solution, let's say, that it fell out of the math. If I take 0 up here, 3 over 0 instantly kills the solution. It goes to infinity. 0 here as well makes another 1 over 0. Basically, if you ever get a solution such that you plug it back in and you get a 0 in the denominator, then that means that that value of x or t or whatever isn't even allowable to be a solution of your equation because it makes your equation explode. It can't be a solution if it does that. So use the technique we're doing here, but just keep in mind that when you multiply both sides by variables, sometimes some of the answers you get aren't going to work. And if they don't work, you say that you have an extraneous solution, which means it's not valid. And you circle the ones that are not extraneous. So in this last problem, we're finally going to get to the heart of the matter where I'm going to show you that. And I've kind of given away the punchline, but that's okay because I don't care about surprising you. I care about you learning. So we have 3 over x squared. Of course, this is going to be a more complicated problem. But it's solved the same way. So we have this guy plus the number 2 equals x minus 4 on the top over here, and then we have x minus 5. All right, so this is a significantly harder looking equation to solve. But you have to remember that the same thing happens. This is a fractional equation because the variable exists in the denominator of these fractions. So what we want to do is multiply by anything to kill this entire term and also to kill this entire term. So let me rewrite it again. 3 over, now I have a polynomial. Of course I can multiply by that, but we always like to factor polynomials. So what we're going to do in the bottom here is I'm going to factor it as I go. Now I'm going to factor it in a second. You still have the plus 2 and you still have the x minus 4 over 5. I haven't really changed anything. X minus 5 on the bottom here. What is this factor to? You have an x squared, so you have an x and you have an x. And then you have 10. Of course you could do 1 times 10. We try 2 times 5. And then, of course, we know 2 plus 5 is 7, so the only way it really works is minus minus. Check yourself. X squared here, you have negative 2x, negative 5x. They add to the negative 7x. And then you have this times this gives you positive 10. So all we've done is rewrite the problem, but we factored the polynomial, which you almost always want to do. And now we have to decide, and it looks like I didn't do a great job with giving myself room. Sorry about that. But anyway, we want to multiply the left-hand side and the right-hand side by anything, by something, in order to cancel this fraction and also cancel this one. So notice we have an x minus 5 and we have an x minus 5. So the rule of thumb is you want to multiply both sides by everything you see on the bottoms, everything. Because the only way that you can cancel all of it is to multiply by the product of everything that you see. So here we have an x minus 5. We know we're going to multiply by that. Here we have an x minus 5. That's going to cancel that one. But we also have an x minus 2, so we have to also multiply by that. So the way you write it is we're going to multiply this by x minus 2 and also x minus 5 multiplied together. Now, unfortunately, I kind of wrote this big, and I'm sorry about that. But we're going to multiply the left by x minus 2 and also x minus 5. And this is unfortunate. I'm sorry about that, but it gets multiplied by the entire left-hand side. So let me rewrite it in a cleaner way in the next line. It'll be a lot clearer. I'll do a better job of writing a little bit smaller. So what we're going to have then, this entire term is multiplied by this entire left-hand side. So it gets multiplied by this and then distributed in also to the 2. So what you'll have is x minus 2, x minus 5. This can be written as a fraction of over 1. Then you're going to multiply it by this first term, which is 3 over x minus 2, x minus 5, like this. Then you're going to have this same thing multiplied by 2. So you'll have x minus 2, x minus 5. This is going to be over 1. You're going to multiply by 2, right? And then I'm going to have this set equal to, I can't fit it all over here comfortably, so I'm going to have this, which will be x minus 4 over x minus 5 multiplied by x minus 2, x minus 5. So make sure you understand, all I'm doing is take this thing multiplied by this thing multiplied by the 2 equals, and then everything on the right-hand side. So now you can finally do what you want to do. The x minus 2 cancels the x minus 2, x minus 5 cancels the x minus 5. And then over here, when you're multiplying by 2, nothing at all cancels. But then what you have on the right-hand side of the equal sign is x minus 5 canceling with the x minus 5. So now we can tidy everything up. This is a giant 1, implied 1s everywhere. This is 1, so all you have left is really a 3. That's all you have left there. But then you have that plus this term, which is all of this stuff, the numerator's multiplied, and then the denominator's multiplied, but you just have 1. So it's 2 times this stuff. 2 times x minus 2, x minus 5. Don't try to do all the multiplication in your head. You just multiply by 2, divide by 1, so there's nothing on the bottom. And then on the right-hand side, you have x minus 4 times x minus 2. Now this is ugly, I'm not going to lie to you, but it's solvable. You know how to multiply these binomials. That's going to give you lots of terms, and then you draw everything to one side and you solve it. So let's first multiply these guys here. So we have 3 plus 2 times. Here we have x times x is x squared. The inside terms give me negative 2x. The outside terms give me negative 5x. The last terms, negative 2 times negative 5, give me the positive 10. On the right-hand side, x times x gives me x squared. Inside terms give me negative 4x. Outside terms give me negative 2x. Last terms, negative times negative, gives me positive 8. So now I have a lot of things to do, but before I can collect terms, I have this, notice I had the 2 out here, so I multiplied this, but I still have the 2. So let's go ahead and distribute that 2 in, so it'll be 3 plus, here we're going to have 2x squared. Now, let's be careful. We have the negative 2x and the negative 5. We can add those. That's going to give us negative 7x in here. But then that 2 will be times the negative 7x, so it'll be negative 14x. 2 times when you add these together, and then the 2 times the 10 just becomes a 20. All right? On the right-hand side, you'll have an x squared. Negative 4 and negative 2 give you a negative 6x, and you have a positive 8. Now, let me just sync up with myself and make sure I didn't make any mistakes. So what I have is 3 plus 2x squared minus 14x plus 20, x squared minus 6x plus 8. Okay, I'm correct so far. So at this point, all you want to do is collect terms, essentially. So let's go ahead and add these together. So you're going to have 2x squared minus 14x plus 20, whoops, not plus 20, plus 20 plus 3 is 23. And you have the x squared minus 6x plus 8. All right, so you have a polynomial on the left and a polynomial on the right. So all you do is you grab all these terms, you move them over to the left by subtraction, so you'll have a polynomial equals 0. So let's do them one at a time. We'll switch colors. One thing at a time. We're going to move this x squared over by subtracting it. So we have minus 1x squared. So 2 minus 1 gives me 1x squared minus 14x plus 23 equals, now it's gone from the right, so we have negative 6x plus 8. Okay? Now in the next step, I'll switch colors again, we're going to move the 6x over by addition. We're going to add it over here. So what we're going to have here, when we add it, is we'll have the x squared. Now we have negative 14 plus 6. When you have negative 14 plus 6, you'll get a positive 8x. You'll have the 23 along for the ride. On the right-hand side, all you have is the 8. And then the only thing that remains is we have to move this 8 over by subtracting it. So we're going to have the x squared. We're going to have the 8x. And then what is 23 minus 8? Over here, we subtract 23 minus 8. We're going to get a positive 15, and that's going to be equal to 0. So let me check. 8x squared, x squared plus, looks like I have a sign error somewhere. You can see where it is. I could erase it and tell you guys, oh yeah, just don't do this again. But I show you, I'm human as well. We have negative 14. I added 6 to it. That can't be a positive 8. It's a negative 8. Right? So this actually is just a simple sign error. It happens to everybody, believe me. So you have a negative here, and you have a negative here. Let me double check myself again. So I have x squared minus 8x plus 15 equals 0. That's correct. So when I added the positive 6, I accidentally made a positive where it should be negative. So now we have to solve this, right? If I just gave you that polynomial something something equals 0, how do you solve it? You factor it, and you have it set equal to 0. So on the next board, all I'm going to do is rewrite that polynomial. It's x squared minus 8x plus 15, and that's equal to 0. How do we solve those? We factor it, right? We have open parentheses, and we set it equal to 0. We have an x squared, so we know it's got to be an x times an x. For 15, you have choices. You could do 3 times 5. You could do 1 times 15. Let's try 3 times 5, which is nice because I know that 3 plus 5 is also 8. So the way it's going to work is negative times negative. And double check yourself, right? X times x is x squared. That's negative 3x. That's negative 5x. Add them together, you get the negative 8x. Multiply these negatives, that gives you the positive 15. So then, this can be equal to 0, or this can be equal to 0. Equally well drives the whole thing to 0. So x minus 3 can be equal to 0, or x minus 5 can also be equal to 0. Notice we're going to get 2 answers because we have a square in the variable. X will be equal to 3. We add the 3. And then x will be equal to 5. We add this guy. So we basically circle it. We say we're done. But then you got to caution yourself. This is the big gotcha I've been trying to mention since the beginning, right? Anytime you multiply an equation, left and right-hand side, by variables in order to clear denominators, you have to be careful, right? You have to look at your solutions and verify that they're not going to blow up your equation. So let's take a look at it. X is equal to 5 is one of our answers. X is equal to 3 is one of our answers. If we look at the original equation was this, but in factored form, the original equation was this plus 2 equals this. Okay? If I put 3 in here, I'll get, which is one of the answers, 3 minus 2, that's a number. 3 minus 5, that's a number. That's cool. You can multiply them, that's going to be a number. 3 minus 5, that's a number. But notice that one of the solutions was 5. You can see right away you're going to have a problem because if you put 5 minus 5 in here, you get something over 0, which means this whole term goes to infinity. And you have the same problem here. 5 minus 5, 0. No matter what is going on here, 0 is going to multiply, give you 0. The whole fraction is going to go to infinity. So basically what's going on here is, if I were to give you this function ahead of time, and let's take a look at its domain, which are the range, it's the domain of the valid values of x that we can use in this function, x is equal to 5 is not even allowed to be a part of this function because it goes straight to infinity at that point. It's a vertical asymptote. So we got an answer of x is equal to 5 only because we multiplied by something that canceled what was on the bottom. So it kind of like, it allowed us to make the equation simpler to solve, but because we kind of removed the denominators, then we have to go back and check to make sure that the answers we get don't actually cause problems in those denominators because we killed them as part of the solution process. So I always wondered, and teachers would tell me that, well, you got to check your solutions, make sure they're okay. And nobody ever really tells you why. It's simply because you multiplied by something that got rid of them. So the new equation we got, which was this one, right? We say it's equivalent to it, but what we really have done is we've eliminated all problem areas in the domain by multiplying it because this equation here, right, there are no problems at x is equal to 5, right? There's no denominators at all. So the bottom line is when we multiply by something to get a simpler equation to solve, it's totally fine to do it. But in the process of clearing those denominators, if some of the answers that you get exist in those denominators, then they can't be valid. Right? Because we kind of used a trick to get the answer to make it easy, we have to check our answers to make sure that they're okay. So what we found is that 5 is not even in the domain of this function. It cannot be a solution of this function. So what we say is that this is extraneous solution. It doesn't mean you erase it. It doesn't mean you did anything wrong. It means you used a mathematical trick to eliminate the fractions, which made this problem much, much easier to solve. But the trade-off is we've got to go, I'm going to draw like a little X through here, even though I don't want you to erase it on your paper. It means it's not a valid solution. It's an extraneous solution, right? So leave it on your paper. Tell the teacher it's an extraneous solution. It's not correct. It's not valid. The only valid solution to this equation is this one right here, because we put the number 3 in, and 3 had no issues anywhere, okay? And if you were to put 3 in here for x and 3 in here for this, and you would do 3 and 3 and just go through it all, you will find that the left-hand side equals the right-hand side with no problems. I'm not going to go through that because I've done it on my paper, but it's a good exercise for you. Put 3 in here, multiply it, add the 2, 3 in here, 3 in here. You're going to find out that it all works out fine. All right? So here we have introduced the concept of solving these fractional equations. So we talked about in the beginning that they're very similarly related to what we did before, fractional coefficients. The variables are in the top, but the bottoms of the fractions are numbers. Here in fractional equations, the denominators can have variables too. So what you have to do is multiply by left and right, often containing the variables that you're trying to clear. But the trade-off of that is that you're going to get answers that you always have to check and make sure they don't cause any problems. If they don't cause any problems going to infinity, then the solution is totally valid. But if they do cause any problems, like we had in that last problem, then you got to mark it as an extraneous solution. It's not correct solution, but it was just part of our technique to get our answer that made it easy to solve. But we have to throw that solution away. It's not correct, but even though it mathematically fell out, and we circle the non-extraneous solutions. As you solve these problems, you're going to find that probably the extraneous solutions pop up in about half the problems. Maybe about a third of the problems you'll have an extraneous solution. A lot of times you won't have it at all. It just depends on the problem and how it was set up. So make sure you can solve all of these. I want you to do all of these yourself, and then follow me on to the next lesson. We have a lot more fractional equations to solve to get your skills to where they need to be in algebra.